So we first start by a small comparison to see where technology is today. If we look at the brain, it's something that weighs a bit more than a kilo, that fits in a bit more than a liter, that consumes between 15 and 30 watts, and has a huge number of neurons. That's something that works pretty well. If you look now at how we can emulate the behavior of the brain, we can have a clue of what it costs in looking at the Human Brain Project, which is a EU flagship project trying to simulate how the brain works. People there have been developing a chip that contains 16K neuron and that consumes a watt. So if you multiply that by the number of neurons in the brain, you see that you will need something like 5 megawatt of power per brain. As a side note, you can see that one neuron costs quite a lot. So you're worth perhaps a bit more than you believe. Anyway, this power consumption is really an issue here. And it's not viable to have something that tries to mimic the behavior of the brain, so we should focus on more specific functions that really are the ones that we feel interesting for applications. So going into what is a neural network, I won't go into that right now, but you have all seen this kind of pictures in which you have the neurons here. And what I want to focus on is the function that is executed by a neuron, which is more or less, from a computational point of view, a vector-vector multiplication, and then a summation on the value obtained after multiplication. This is quite important because a neural network is learning. There are two phases when using a neural network. Learning, when you train your network to, for example, classify some things, and inference, when you put a new value in front of your neural network and it will produce the class to which it most probably belongs to. And here, what is learned during learning are the weights, the W, I, J here. And these weights are very important because that's what the neural network learns. Here, the computation itself is quite simple. But the issue is that we have a lot of these computations, specifically in deep neural networks. You will have a huge number of computations. And also, you will have a huge number of weights. So the issue here is really how can we do inference without consuming too much energy. This chart shows on the x-axis the number of giga operations that a network needs. Here, the accuracy of the network, and the size of the bullet here shows how many parameters the network has. And as you can see, even the more efficient and smallest network have more than 5 million parameters. And we cannot see here exactly where it stands, but it's around 0.5 gigaops to perform inference. As you can see, there is quite a lot of different architectures for neural network because they are targeting different applications, and also the research has focused on trying to reduce the number of operations and the number of parameters. Even so, this has made some progress in terms of doing inference on the edge is really still an issue. So as Alice just said, what's the interest of doing inference on the edge is that we are doing local computation. And among the things she did not talk about was energy, and it's the main focus of this talk. So energy is very important here because you don't have to access a router, a cloud server somewhere. So in terms of energy consumption, you will have to do everything locally. And you have to be aware also of the fact that transmitting data through a wireless or wired interface costs anyway energy. So it's always a trade-off that you have to find between sending data or doing it locally. Here we are really focusing on doing it locally, but we have also this latency problem and privacy because you don't want your vitals to be sent somewhere on the cloud. So let's have a look at what are the challenges in doing hardware acceleration for neural networks. The constraint we have is that first, accuracy is really depend on the application. So there are some applications for which accuracy is not so important, and on the edge, quite a few of them somehow can perhaps be accuracy can be trade-off here. In terms of silicon resources, we have the computations to perform and the weight to store and access. So that's the thing we need to put on our hardware, and under specific energy constraints. So if we look at the typical constraint that we have, if you are looking for a wearable, for example, you would have to 10 to 100 microwatt of power to do what you have to do. If you look for phone, it's something like 10 to 100 milliwatt. And if you are looking for plug device on the edge, it would be something between 1 and 10 watts. So the energy budget is very restricted for most of these applications. So let's have a look now at why the energy, where the energy is spent. First of all, if we come back to the chart I showed with the neural network architectures, we can see that we were somewhere between 0.5 and 40 gigaflops to be done. And so gigaflops are floating point operation. And if we look at these data here, so you don't have to go through them. But the important thing here is to see that when you have some FP, this means floating point, and you can see that the bars are always bigger when you are using floating points than when you are using classical integer arithmetic. And here, this is a log scale, so any even small change, indeed, implies a big change. So this is true both in terms of energy, but also in terms of area. And on the edge, the square millimeter of silicon is something that is very sensitive, so you have to be careful about that too. So the bottom line here is that floating point operation are energy and area costly, and we should avoid them. Not only we are doing floating point operation, but we are also accessing a lot of memory. As we have seen, quite rapidly on the chart, but now I can focus a bit on it. The number of weights that is necessary for a neural network to work well is big. If we take some recent example like Google Lenet, we have 4 million weights. There are 64 bits on floating points, which means that you have 4 times 8 equals 32 megabytes of weights that you have to store somewhere. And if we go to VGG, it is just huge. So when you have this number of weights, you cannot live with only local memory inside your circuit, so you have to fetch the data outside. So this is typically what a system with a neural network accelerator works. You have some processor here, the accelerator there, and he's doing accesses either in static memory locally or in a dynamic memory outside of the chip. And when you look here at the energy cost of local access in the static memory here, it's something that costs something like 2 floating point operations. But when you look at the DRAM external access read, then you have 2 orders of magnitude energy penalty. So it's really very important not to be to go fetch weights outside. Oh. Okay. Oops. So this is just the end. So, okay, it accumulates the clicks. So what are the alternatives when we want to go to hardware-friendly operations? First, we have to change flops for something else. Most probably, we'll trade computation power for some accuracy. For that, we will simplify the operation. First of all, we will not use complex activation functions, nor batch normalization and this kind of stuff. And as FP arithmetic is not hardware friendly, we will use data types that are not floating point. In terms of memory and usage, we will trade bytes for accuracy also, using small data types with a small number of bits, and we will integrate many memory cuts with the processing elements in order to have the data that is close from the computation. And there is even a trend in integrating directly the computation inside the memory, and we will come back to that a bit later on. So the typical acceleration architecture that we have are the following. Either we have an accelerator here that is using classical memory, or we have accelerators that have memory locally and a lot of processing elements that are just doing multiplication accumulation, I would say. Or you have the memory that contains itself both the data that is stored and the computation that you have to operate on the data. So these are the three solutions that we have in terms of implementation. First of all, independently of the solution, the architectural solution we choose, there is one important thing to have in mind is that quantization is something we need to do to reduce the size of the number of bits over weights and activations. And people at Xilinx have been doing some research on that, and they have shown that in terms of computation resource versus accuracy, you could live with something that varies between 1, so binary, and 4 bits to store weights and activations. To do that, you still have to do some retraining. You cannot use your classical neural network training approach. You need to do some specific stuff there, and you also need to enlarge a bit your network, but the gain is just large. So a few hints on the classical, I would say, with the accelerator here, accelerator architecture. Here we have an accelerator that will be suited to do a specific part of the neural computation. In that case, this work is presenting a custom sparse matrix vector multiplication, and it relies on the fact that the data are stored in a specific way for the matrix and the vector. So it will eliminate a redundant connection that would exist in the neural network, and it uses quantized weights. So this allows to, and the quantification is 4 bits per weight. They can show that using this specific representation, they can avoid a lot of computation and reduce reduce the number of weights they need. And at the end of the day, the energy efficiency is much better than a solution on GPU or CPU. But still, here we are still using 600 milliwatt just for the last part of the LXNet network. So people have been pushing a bit farther. Instead of using 4 bits, they are trying to use only 2 bits, to use ternary weights. Ternary means balanced ternary means -1, 0, and +1. So here we still have to have the floating point accumulation, but there is no multiplier anymore. And furthermore, when you look at what are the values of the weight, you can see that in average, for the inference part, you will have something like 20% only of the weight that will be non-zero. So doing some specific hardware to skip the 0 values brings you a very good efficiency. And so using this approach, they can divide by 3 the number of floating point operations. So more or less the power that is necessary, the computational power necessary. Pushing a bit farther is, instead of using ternary, let's use binary. So in that situation, it's more or less the same kind of approach that is used. This is a VLSI implementation of a binary weight CNN accelerator, work from ETH Zurich. So here the idea is that multiplying by -1 is doing the complement, multiplying by 1 is just passing the value, so you can replace multipliers by very simple circuits. Still, you need you will still need normal accumulators. And in that situation, they were using a 12-bit activation to have the required accuracy. And 12-bit activation is still quite a bit. Also, there are a large on-chip memory, which is based on a latch. So it's quite easy to implement in terms of VLSI integration, but it's not so, so cheap in terms of circuit area. Anyway, they have a flexible accelerator, and an important metric in looking at what an accelerator can do is the number of tera operations per second per watt, and they reach above 60 tera operations per second per watt. And please note that here the tera operation, the T is tera binary operation, so it's not typically floating points. So, going still farther, people at Xilinx have been working on the FIN framework. FIN is a binary neural network accelerator. In that case, everything is either -1 or +1, the weights and the activation. So, when you look at this architecture, you can see that doing the multiplication between 2 bits can be done only using one exclusive OR gate, and then a pop count, and then you can just accumulate on a very small size. So this gives you very efficient hardware. There is one thing important here, is that you have to learn not only the parameters of the network, but also the threshold memory, because your accumulator will produce a value that you have to decide if this value will be 0, it will be -1 or +1. And so this weight memory takes some space, and you have to learn these weights. So a similar approach using here not binary values, but ternary values, both for activations and weight, leads to a better result in terms of accuracy. In the previous case, the accuracy was, the error rate was around 20%, and it's a bit more than 13% in that case by using -1, 0, and +1 for all situations. Anyway, both these approaches are implemented on FPGA, so that these are reconfigurable logic fabrics that are not so energy efficient, but they are proof of concept that this kind of approaches can really be useful in terms of energy sparing. On a typically different approach, there is the True North chips from IBM. And True North is working on spiking networks, spiking neuron, excuse me. So instead of encoding the data as value, you encode it as pulses. And so there is a way to handle these pulses. And the interesting thing here is that something will happen only when a pulse occurs, and not on every clock cycle. So there is a potential for gaining energy that is quite interesting here. And this has been fabricated as a chip by IBM, and it's a very large chip. And okay, it runs at the 46 gigasynaptic operation per second per watt, so it's quite impressive. Finally, there are these processing in memory approaches. In that situation, what we are doing here is have the memory point here, because when you are storing a value in memory, it's in a specific point. Here you have a word, I would say, and here you have a bit. And what do this memory? In fact, they are just, here you put your values, here you have some kind of a transconductance, which is the inverse of a resistance, and so you can read out here currents. And so, given if you are able to choose the right value for this transconductance, then you will have the current here that will be the sum of the product of the voltage here and the transcondistance here. And so this, if you look at this equation, that is the result of what's going on here. In fact, it looks exactly like a vector-vector multiplication, which is exactly what a neural network needs. So here, the synaptic weights are not stored in outside memory, but very much at the point where the memory is. So it's a huge, it has the potential of having a huge reduction in energy consumption. So but now we are doing analog computation, which are intrinsically approximate. So it's not so easy to exactly program them. And also the circuitry around is not that easy. So it's quite forward-looking in strategy. But even so, it has been shown to work. It has been demonstrated, I would say. So it's not a large-scale stuff, but it's something that shows that it has potential. And this was done on a specific CNN using the well-known MNIST benchmark. And so they were able to indeed recognize the value using this approach and the analog computation. Last but not least, in terms of potential, there are these new emerging technology that have a behavior that is a bit close from what the neuron, how a neuron would behave. And here, so you have spikes that can be sent on this memory. And the fact of sending spikes will change the crystal nature of the memory point. And so it will behave more or less like it will change from amorphous to crystalline and back and forth. And so it will take the right value, getting a set of pulses in the input to produce also a set of pulses at the output. So this strategy is quite interesting because it goes to very nanometric scale. And there is a huge potential for very dense neural networks using this approach. And here also the computation is redone at the very place where the memory point is. So this is very prospective, I would say. So it's called neuromorphic architecture. But anyway, it's something that has potential and people are looking to it because it can bring a huge reduction in power consumption. So this is just an example to say that, okay, this has been a prototype and shown to be able to do some stuff, but as you can see, it's still at very small scale as compared to what normal CMOS technology can do. So as a takeaway, I would say that today we have some solution for inference at the edge using a classical digital CMOS technology. First of all, quantization and compression is the way to go. We need that. We need to go at a very low bit size. But we have to have new learning approaches for that. And the network and architecture are available today. Just at the beginning of the year, there is a book that was just published by people from Google, which is called TinyML, and presenting algorithm suitable for microcontrollers. So I invite you to take a look at this book because there are very interesting solutions for the edge also. At the end, we have processing in memory approaches, and these processing in memory approaches are still quite being discussed, but they are promising and an ongoing research subject. Thank you.